There's on the front. I think the last one. Better last one. I haven't done the last one. I got tired of it.
All right, I have to get started. If you look at the schedule, you'll find out that there's a midterm exam this Friday. So don't have that much time to work on the new tutorials this week. It's very short and easier compared to the last one. So in the midterm exam, there are only two problems. The first one is the Arduino programming problem. So you need to have your Arduino with you. And another one is a PCB design. So you need to design the self-defined library from a device you have never used in the past, and make the schematic and also the PCB layout as well. So two problems in 55 minutes. So you want to familiar with PCB design workflow, and they're not very difficult. Since we're only 55 minutes, I'm not expecting you to complete a very large scale project. So it should be a very simple and basic two problems. And next week, it's a commercial robot car. So I'm going to give the car to you. You don't have to design any of the hardware. So it's very straightforward. So just complete the programming and let the car track the black line, use the remote to set up different modes. For example, if you press 1, it's going to start the line tracking. If you press 2, it's going to start the self-driving. So you can use all these keys to drive the car. And if you press number 3, it becomes an obstacle avoider. So just repeat the work I did over here. Because you don't need to design any of the hardware, that's why you only have 1 week to work on it. If you want to work on it during the break, just feel free to do so, but I didn't plan on that. So you can see that it's due right after the spring break. But you also have 1 week before the break to work on it, all right? And then it's a relatively larger scale project. So that's an Arduino controlled temperature sensing with the IoT network, Internet of Things. It uses the ESP8266 to send the data to where? To ThingSpeak. All right. So the data can be logged into a commercial website, and you need to design the PCB out of as well. Right. And then it's another larger scale project, has 2 tutorials. This is another product I developed for a company, but I didn't include all the materials in here. So it's easier, simpler version of it. So 2, and you need a PCB auto as well. So after this class, you'll be an expert on PCB design. There's so many PCB. So this class is really hands-on, compared to other courses. And then I want you guys to try, 2 other microcontrollers, not just the ESP32s and Arduinos, but also, MSP430 from TI, Texas Instrument, and ST32, which is very popular in the industry. And then final exam. That's the plan for the week, for the semester. Okay, let's get into this tutorial. See what's going on here. It's a PID controller. Looks complicated, but actually very simple. So we are just trying to use Arduino code to implement this algorithm over here. So the input to the Arduino system is a set point. So if you set that point, which is a goal, to let the Arduino to reach that goal, and after it processes the error, and it's going to output the actual value and compare to the set point, do the subtraction, and see how long or how many iterations still need to be executed in order to reach that goal. So until the subtraction 0, it's going to stop the process. And these are the three functions to process the error. So you can see the set point here minus the actual value. So there's a gap, so which is an error, and it's being processed by the P, I, and D. So P is a proportional, so it's just use a constant to times the error, and I is integral, D is differential. So these are the three functions to process the error and eventually get the current value, and then being fed back to the input and to the subtraction again. So it is able to do the feedback very quickly because it's a digital system. So until you are getting a 0 for the subtraction, it stops the execution. You know, there are so many difficult or complicated examples we can practice with a PID controller, but I just find out the very easy examples that I can do on the board really quickly. So it's just a 1 week project and not a 4 weeks project like what we did in robotics too. We used the PID controller to control the angle of the car, so the two-wheel robot car can stand steady on the table because it's controlling. Whenever it's leaning forward, it can do the subtraction and find out the error angle, and then move the wheel to that direction. So it is able to stand on the table. It's a 4 week project. We only have 1 week. So we're going to use a sensor. It's a thermistor, not thermistor, sorry. For LDR or photoresistor. LDR means light dependent resistor. So if this sensor is totally in dark, then the resistance is over 25 megaohms, or sometimes 10 megaohms, 20 megaohms, depends on the model of the LDR. But if you shine very bright light onto it, the resistance can be as low as 1K, 500 ohms. So this is a light dependent resistor. You should have it in your box. If you don't have it, I have millions of them in the drawer. I'm gonna give you one. So you can see that I use a pull down resistor. So if I don't have any light shines onto the LDR, for example, and I have this kind of circuit, what is the voltage here at this point? What's the voltage should be here if I don't have a LED here? It's totally in dark, for example. Why 0? Yeah, resistance here is so like 25 megohms, and the 2K and 10K is like a short circuit. So the voltage is being shorted to the ground, right? So it's 0 volts. But if you shine light onto the LDR, what's going to happen? What's the voltage here would be? 5. This becomes a really low resistance resistor, and it's going to short this point to 5 volts. So it's become 5 volts. So you can, the light shines onto the resistor, changes the resistance, and the change is being reflected to the voltage over here. So you can use the A0, which is the analog read pin on the board, to read the voltage, which can reflect the resistance change over here, right? So high resistor, low voltage. Low resistor, high voltage, right? And then on the board, you need a little LED and definitely a resistor to protect the LED. And you don't want to put the LDR on one side of the board and the LED on the other side of the board, so it's not affecting anything, right? You want to put them really close to each other, but not short it. You don't want to have the pins to contact with each other. And what I'm doing here is, because it depends on where you are doing this experiment. If you do it here in this room, you want to always do it here because the ambient light intensity will change if you move to somewhere else. But it's also okay if you change the location, you want to recalibrate the value, the offset value, which is like if you don't turn on the LED, what is the default light intensity in the room? So that's why I did over here. I didn't turn on the LED just to do a very simple analog read from the pin here, right? I don't have the LED yet, and I just directly have this circuit. So I'm reading 677. One quick question. Stronger light, higher voltage or lower voltage? Higher voltage. So stronger light, higher voltage. Right. I didn't turn on anything, just use the ambient light in the room, and I'm reading 677. Right. That's if you don't do anything, it's gonna show you this intensity over there. Another quick question: can you dim it? Yes, you can, but it's very difficult, right? In the room, how to dim it? You have to cover it with our hand. It's very difficult to control. Sometimes your hand has some openings and your fingers. So we are considering that we cannot dim it. This is always increase the light intensity. So 677 will be the highest or lowest intensity you can get. Lowest. Because you turn on the LED, it's always getting stronger light, right? So this is the dimmest number you can get. And then you turn the LED fully on. Here you turn it fully on, make it really close to it, right? And then turn it fully on. And then you read it. So that will be the brightest signal you can get, right? And you see what I do here? So look at your board. So if you look at the digital pin of number 3, actually it's on the right-hand side of the pins in that column. All these pins are digital pins, right? Because you can see it's a digital parenthesis PWM and a symbol over there, right? But not all of the pins have that PWM function. So what is PWM? Pulse width modulation, all right? So the way you change the brightness of the LED is using pulse width modulation, because you cannot directly use a digital signal to control the brightness of the LED. Why is that? A digital pin can only output 0 or 1. It's all just on and off. But if you use the PWM, it's pulse width modulation. You can make it like that, or you can change the duty cycle to make it like this. All right. So these are the output signal from the digital pin. And if you do an average power from the first one, it's probably over here. If you make an average power of the second one, probably it's a little bit higher, like that. So you can use the PWM. It's oscillating really quickly. The first one has a lower duty cycle, but the second one has a higher duty cycle. So you can use the average, the difference of the power to control the brightness of the LED, but not the digital pin, because the digital pin is only on and off. It's pure 1, pure 0. It's not controlling the brightness. You have to use PWM, and not all the pins have the PWM function. If I have to look at the little symbol on the pin, so you know which one can be used as a PWM output. So number 3 is one of them. That's why digital write, you can write a 255, but not a high or low. So 255 indicates that it's the highest duty cycle. Why? Because it's an 8-bit, 2 to the 8th is 256, right? So you have 0 to 255 as the range. And these are the 256 options you have. So you can use either 0, it's going to be totally off, or 255 will be the very high duty cycle. So that will be the brightest signal you can give to the pin. or to the LED. Would that be the same as just to put a high here? I think it's going to be the same value. But why we want to use 255, not high? Yeah, it's going to change it to 200 or 150. It's going to have all these continuous different steps, right, of the intensity. If high is just high, low is just low, right? You have so many options over here. So I'm trying to turn it on and then read the intensity and print it. So what's the problem here? What's the problem here? So the lowest is 677, the highest is 734. Sounds not right. So that's such a very small range. I mean, what's the problem of the code over here? See what I'm doing? I want to test the brightest signal I can get, right? So I'm writing a digital high, I'm turning on the signal, and then read it. I turn it on, turn on the LED, and then I read it immediately, and then I print it out. I'm thinking I'm getting the brightest signal I can get. What's the problem of it? You need to delay because Arduino is not really fast and high-end CPU, but it's still running at 16 megahertz. So it's running the first one, and then after like 1/16 megahertz, that I don't know, like less than 1 microsecond, you can run the second code, right? So the LED is not fully on yet, but you are reading the analog data from it. So you want to delay for like 1 second, so that when the LED is being turned on, fully on for a while, and then read the analog pin, so you can get the brightest signal, which is actually 924 after you add the delay. So it's different, right? So you know that lowest is 677 and highest is 924. And here's a PID script, and it's not perfect, and I had some little problems, but it worked. So I'm going to let you know what are the little issues here. So first, I didn't use IND at all. You can have KP, KI, KD on the top, but you don't have to assign gains to each of them every time. So I'm only using the proportional controller in this example because all these parameters are zeros. Whenever they times the error, it's going to be 0. So it's not contributing to the controller at all. So these are the errors, PID errors, and these are the gains. If you look at the diagram over here, so that's a P error, I error, D error, and these are the gains, the Ks. You just need to implement this function over here, okay? So make this one, make this one, make this one, add them together, and that's the final value. That's it. Now let's come back to here. Because the lowest is 600 something, the highest is 900 something, so I made the set point to 800. So I know that if I not turn on the LED 100%, but it's going to reach 800 because the highest I can get is 900 something. So I'm pretty sure 800 is reachable, right? So I can use 800 or a little bit more than 800. It doesn't matter. It just needs to be in the range, within the range. So the best value you can pick up is in the middle, right? From 600 to 900. Pick up something in the middle. And so for the first example, I used the set point to be 400, and just trying to show you that it won't reach that set point at all. Because the lowest is 600 something, right? You don't have the dimmer. You cannot dim it. So if you set the set point to be 400, you can see the result becomes always 800 something, right? So it can never reach 400. So I have to change it. So I'm asking you to change the number here and fill in the crossed out code over here, which is actually this one. I just put it here, and you should be able to So the sensor should be able to reach 800. And that's the first example, very simple. And the second one is adding another LED here. So I have another one, what I'm trying to let you demonstrate is, so this one doesn't have a switch. So if I turn on the power, it's always on, right? It's always on. It's adding photons to the sensor. And if I press, I got another LED very close to all of them as well. If I press the push button, what's going to happen? If you have a correct PID, have a functioning PID controller over there. So what's going to happen? Since I have a set point, right? Yes. And what's going to happen? So this is being controlled actually. It won't turn it off, but it's going to dim it. Because one is adding photons to it. So the other one is being controlled, right? So it's going to be being dimmed by the microcontroller. So the overall photon being received by the LDR is still 800. Right. So here is a demonstration, and let's see if that makes sense. So the blue line here is a set point as a constant. And this is definitely very noisy, so you'll know that it's a signal received by the microcontroller. And if I press, so at this time point, I pressed the push button, and the signal being received by the controller becomes higher, right? Is that making sense? Because it's getting more photons, right? But here's a set point. It's a constant. I just use a constant. I just plot the constant over there, right? It's not going to change. So what's happening here? It's dimming the other one. Still trying to reach the set point, right? And then I release it at this point, okay? I release it, so I fully turn off the other one, so you can see the number of photons will be decreased significantly, right? That's why you are seeing this, the dip. But why is getting back? I didn't push the push button again, right? So why is getting back? So the other one is getting brighter because the controller is changing the PWM value over there to make it brighter, right? It's still trying to reach the set point. Why is so slow? It should happen immediately, right? But push it, it should track it really quickly, but it's not. What's the problem here? The gain. So I only used this one. I didn't use these two at all. But you can see it still works. Sometimes it still works, not perfectly. For this simple example, it's okay. But for the balancing card, you have to use I's and D errors to avoid overshooting and to avoid all these really slow tracking. So what's the gain I used for that example? I only used the 0.001 for the gain. So it's very slow. If I change it, I changed the gain, the proportional gain to 0.1. So what's happening here? What's intuitively, how do I understand the PID controller? What's really happening? So for the proportional controller, is the easiest one, right? So for example, the set point is 800, and the actual value is 600. Okay, so so the controller did the subtraction. So the error is 200 now. So how many do we want to add to the final result to reach 800? Now it's 600. The set point is 800. The subtraction is 200, right? You actually don't want to directly add 200 because it's going to oscillate. For example, it's always adding little ones really quickly because the digital system, right? It's doing the feedback. So it's always adding this very quickly and then to the set point. You don't want to directly add 200 because usually it won't be that accurate. Because for example, the gain only, you times the gain, it only allows you to add 201. You're not getting 200 at all, right? So it's adding 201, so it's overshooting, right? And then you do the subtraction and find out it's too much. So it has to subtract 201, so it's get back very badly. So they're getting way lower. So we don't want the change to be that much, that it's just too much every time. You just want to do the little ones. Overshooting is still subtracting the little ones as well. So you're not like doing oscillating like that. All right. It's a gain. It's not 0.1. It's 0.001 times the error. All right. So that's the gain of it. So you can imagine that why it's so slow, because it's keep adding all the little ones. The gain is too slow. It's too small. It takes so much time to reach the set point. So if I increase the gain by 100 times, so now the gain is 0.1, and you can see the response time in this example. See how fast it is. Do you realize that? So if I press the key here, right, and it overshoots, why? Because I'm adding another LED to it. And why it's going back so quickly? Because it's dimming the other LED really quickly as well. And then I release it later. It's also responding really fast. Okay? Make sense? And in this example, I have a push button detection. It's a key detection program. So whenever you press the push button, it's going to detect the rising edge. And then every time you push it, it's going to add a number like 10 or 20 to the set point. So your controller should actually track that change all the time. So it's actually changing the set point. So if I press it, you'll see the constant is being changed, right? And the intensity of the light is tracking that set point. If the controller is working properly, right? And then you press again, it's still tracking, right? And you want to demonstrate this example as well. A quick note on the push button detection code. So I think you are seeing very similar example in embedded system as well. It's using a different debouncing program. It's bouncing back and forth whenever you push the push button. Why? Because it's a mechanical material. It's a metal plate over there. If you push it, it's actually, you couldn't see it, I feel it, but it's vibrating really quickly, back and forth. It's turning on and off that switch really quickly, actually. But the question is, why you couldn't see it when you push the push button and turn on the LED? So you have a board, right? I'm telling you that if you push the push button, what's happening over there is it should be turned fully on, right? That's ideal case. But actually it's not happening in that way. What's going on is it's vibrating like that and then eventually turn on. That's what's happening in real world. Because it's a metal material. When you push it, it's like bouncing back and forth and then being stabilized. That's what's happening in the real world. But when you are turning on the LED while you are not seeing, the LED is blinking. Yeah, it's so fast. This bouncing back and forth, this frequency is probably over a few kilohertz, right? You couldn't see the LED blinking because it's too fast. For LED, it doesn't matter. You just want to turn it on. You push it, turn on, right? It doesn't matter at all. You don't need a debouncing circuit to make it a perfect rising edge. But however, when you are relying on the push activity to do something, right? You just need a one rising edge. But however, if you don't do a debouncing circuit or debouncing program, you'll see how many rising edges are happening over here. Many. Okay. What I want to do is I push it once. I only want to add a 110 to the set point. That's why you are seeing is only increasing by 10 or 20, whatever you want to do, right? It's only incremented by once, but not so many times. So for that project, it's actually sensitive to the bouncing. So what you want to do, you want to make a debouncing program. You can do it in the software or you can do it in the hardware using a latch, but we don't have a latch, so we are doing it using a code. So this is a very common debouncing circuit and why it doesn't work for this problem. So what this does is actually, if you sense a high here, and then delay for a period of time, and then sense it again, see if it's still high. If it's still high, then it's stabilized, then I want to say it's okay. Why it doesn't work for this case? Hmm? Say it again?
Does it not wait long enough?
That's what I'm thinking, actually. Delay for 10 nanoseconds, 10 microseconds, because the unit here is 10 microseconds. And then if it's still high, then do this, right? I forgot why it didn't work. Yes, you can increase the delay time here. So if it sends the high, no. Yeah, because for example, it sends the high here, right? And then after whatever, how long, right? It's still high. So they keep adding 10 to it. You know what I mean? You cannot, your finger cannot be that fast, right? Cannot be that accurate. You are trying to like, so you don't have a long high here. You don't have a long high here. But you couldn't control it, right? How can I control it fast enough? But you know, the Arduino is running at 16 megahertz, is like sensing all these highs really fast. So you can never do it. So what's happening here is it sends the high, right? So yes, it sends the high here, right? And then delay for a period of time, like 100 microseconds, for example, and sends the high again. So let's add to it, right? But it's always running back and forth. It's going to sense a high here as well. And then after a while, your finger is still on the push button, it senses another high. It's going to add another 10 to it. You have a too long high afterwards, after the bouncing, right? Did you get that? So there are so many highs. It's a constant high. It sends the high, delay for another like 100 microseconds. Your finger is still on the push button, it sends another high. Just keeping adding one. So that's why it doesn't work.
What if we just put the behind it? So instead of looking for high, we have to look for low. And so is it still bouncing whenever it comes off of the button?
How do you want to do it? Sense the for low and
yeah.
So if you don't push it, it's going to be low, right?
Yeah.
So it's the sensing low.
Right.
And then
what if you just connected it so that it's always high? But if you push the button.
Well, couldn't you do it so like if it's all low, then nothing happens, and then like.
So the problem is just the high is just too long, and it's not controllable. It's auto control. So what's happening here is you only need a rising edge. You only want to detect the rising edge. The rising edge is just happen once, right? If you detect the rising edge, done. Even though the low is so long, the high is so long, but you are only detecting the rising edge. So let's see the example here. I think what I did is you have a current state, right? And you have a last state, okay? So whenever the last state is different from the current state, which means a pushing activity is happening, right? And then the current state has to be high. So why that works is because, for example, still the same example, right? It bounces back and forth, okay? It must be different. So the state must change. So I have a last state, whatever the last state is, and in the end of the code, I assign the current state to the last state, all right? So when I'm going back to the top of the code, whenever the last state, I'm still reading on the top. I'm still reading the status, which is the current state. So when the current state is not equal to the last state, which means there's a rising edge. And the current state has to be high. So that's a rising edge detector. So the question here is, why the following highs are not being detected? Because the last state, it always equals to the current state. So it won't get into the if statement because it doesn't satisfy the condition. So in that case, you can detect the rising edge only, but not the state. Make sense? So I gave you the example here, I think. So see, it's always sensing, and you have to put the sensing code on the top because it sensed whatever the current state is and assigned the value to the current state. Okay, and at the bottom, you assign the current state to the last state because next time it's gonna come back to the top. So the old current state becomes the now last state, right? And whenever it's different and the current state has to be high, I can call it the rising edge. So you can use this code to debounce the push button. Okay, so when you are working on, sorry, because you guys are in both of the two classes, I'm just going to confuse you guys. So when you are looking at UART, which is next week's, actually this week's, I'm going to do the introduction on Tuesday. So there's a debounce code here as well, see? It's being implemented in a totally different way, right? I'm going to talk about it on Tuesday. Right? Yeah, I think these are all the things I want to talk about. So again, this example code is definitely not perfect, and I think first, for example, I didn't use the integral and differential errors at all. I mean, you can definitely try it at a different gain there. And also, this is different. This is wrong because in C++, if you want to add error, add something to it, right? So it's going to be I plus equal error, not I equal plus error. It's a syntax error here. But since I didn't use the KI gain at all, so it didn't affect the result. And I think I just didn't have a time to revise this tutorial. It's not perfect, but you can refer to the other students' reports from 2 years ago as a reference, definitely. Yeah, I'm looking forward to see what you can get on your side. And that's everything about this tutorial. It's very short. You don't have that much time to work on it. Keep in mind, midterm exam on Friday, right? Open book, open notes, open everything. Open internet, but just do not communicate. cannot cheat, but other than that, you can, search for answers somewhere else. But definitely, you cannot search for a, directly answer from the internet because it's a very specific problem. Right? Any other questions? Do we need a cable, VGA cable?
I think so.
Yeah. Mm-hmm.